Yeah, cool. Let's see. Okay, so I can plug this in. I do want to change the video to
All right. Can you guys hear me? Is it loud enough? I feel like it's not that loud. Yes? Okay. So we've fixed the Zoom, so now everyone can get in and we will also have chat. So if you want to chat, join the Zoom. The updated link is on the website. There we go. Okay, cool. So yeah, sorry about that for last week. We should all be able to now get into the Zoom without any limits. Yes, we're over 300 now. Awesome. Okay, good. And I'll do my best to monitor the chat on the side here. It's got a lot of stuff going on, but we'll try my best. But yeah, feel free to ask any questions there. Hopefully it'll be a little bit more collaborative, so everybody can kind of answer each other's questions for them. What happened to John De Niro? He'll be back. Don't worry. Oh yeah, captions. Yeah. Live transcript. Is that what I want? Okay. All right. Good. Cool. Sweet. So a few announcements today. Lab 4 is out, due Friday, homework 3 due Wednesday, turn it on Tuesday, so kind of normal stuff. One thing that's kind of new is we will have our first project released this Friday. So as we kind of mentioned at the beginning of the semester, project essentially just a longer homework assignment. It'll take you about 2 weeks than 1 week, and you will be allowed to work with a partner on this if you want to. You don't have to, but you can. So you'll find out more about this kind of in your sections, and you'll get more details about this on Ed as well. So just stay tuned for that. And then one minor update for my office hours, I had to change them this morning. So sorry if you went to the wrong place. They're now on the north side of campus rather than on the south side. Still the same time, 11 to 12 on Mondays, but come to VNA. That's where I'll be doing them now, every Monday. Cool. So where are we now today? So I guess looking back over the last week, we went into our first time creating visualizations, which is pretty cool. We went really deep into actually loading data from a spreadsheet into a table, manipulating the table, and then finally actually making some charts for the first time. And today we'll talk about certain kinds of charts and visualizations, which are really, really important in statistics and all of data science, which are called distributions. We'll learn what is a distribution today, how can we actually visualize it. There's going to be 2 different ways that we do that. And that's going to be the main kind of crux of today's lecture. And then on Wednesday and Friday, we'll switch gears a little bit from visualization, do a few more things in Python that we need to cover before we go to the next part of the course. So it'll be a little bit of a mindset change, but today will be like more just visualizations, kind of like Friday. So before we continue with that, some terminology that we should go over. So this is all going to be the context of essentially tables and data that we are always going to be using in this course. So we've already talked about attributes a little bit. We talked about how that's essentially just variables. So those are just columns. So when you see attributes, think columns. And then when you see individuals, you should think rows. So individuals are kind of the entities whose attributes are being recorded. These could actually literally be people, but we saw an example where this could just be movies. So each movie is a different individual. That's also fine, right? So it's not necessarily talking about people, but really just every row of your data set of your table is some sort of individual. And then we're measuring some attributes about them. And then we'll try to typically visualize charts that convey the relationship between 2 or more of these attributes. That's typically what we're going to be doing. And then new terminology, which we've kind of been using, I guess, accidentally so far, but a variable is really just an attribute. We call this a variable because typically you have people having different values of this attribute in order for it to be interesting. So, if you're measuring something like age or the gross earnings of a movie, that's something that's going to vary across all of our individuals. That's what's called a variable. And again, variable, attribute, column, all the same thing. And then we talked about on Friday that there's going to be mainly 2 kinds of these variables that we're going to be looking at in the course. Either they'll be numerical, so numbers taking on sort of infinitely many possible values, or categorical, meaning that they're from a small set of categories. And then this is really important, which is that for each of your variables or attributes, your individual has exactly 1 value for each of them. So if I'm doing let's say a survey or something, and I'm asking some questions, they're going to have exactly 1 response for each question. That's essentially what that means. So if I ask for your age, you should be telling me 1 age. If you tell me the earnings for this movie, there should be exactly 1 value for that. So exactly 1 value, that's really important. And because it has exactly 1 value, what this means is that the entire column, that entire variable, has something called a distribution. So what is a distribution? It's essentially just saying that you take all the unique values of that variable, and then you count the frequency that it comes up, each unique value. So for example, if I have our data set of the movies, and one of the variables is the studio that made the movie. And so we saw how there's multiple movies made by the same studio, obviously. And so if you go down the entire table and you look at all the unique studios that show up in this table, take that list of just unique values and then count up how often each one appears in the table. That is a distribution. So it's just list of unique values, how often it appears. So we have MGM appears 5 times, and then we have Paramount appears 10 times, and so on. So that sort of list of 2 columns, that's just a distribution at the end of the day. And you can define a distribution for your categorical variables. You can also define a distribution for your numerical variables. Those require a little bit of extra care, but we will cover that today. But in essence, that's really what you're doing, is you're just trying to get a sense of how does this variable actually vary, what values are more common, which ones are less common. And you get a picture of that with this summary, which is called distribution. So here's an example of a distribution. So this is a question that was asked in a survey. basically they ask like, how often do you go online? And so the possible responses you could have had to this question were like almost constantly, several times a day, about once a day, several times a week, less often, or just never. So you're just like never online. And so this was asked to, some set of US adults. And the responses that we got, what we're seeing here is essentially all the unique possible responses you could have given. So in this case, there's really only 6 possible responses you could give. So these are the 6 that I mentioned right here. And then the numbers that we see, those are the frequency or amount of time that people responded with each one. And this is essentially just a chart that visualizes the distribution. And so you can see which ones are more common. So several times a day is the most common answer. Then you have almost constantly, which is like the second most common answer, and so on. And so this just allows us to actually sort of summarize an entire column. So you can imagine this entire data set is maybe like several respondents who responded to the survey, but we've now summarized that entire column with just a few numbers here. That's what distribution allows us to do. And then one really important thing about your distribution is that all the numbers, if you consider them as percentages, they should add up to 100. And that basically says that like the chance of some sort of response needs to be 100%. Like you need to respond to something. You need to fit into one of these responses. And so if that's not happening, then you're not actually looking at a distribution. So that's really important. Sorry, there's just some feedback on the mic. The volume down a bit. So here's an example of a question, or just really a data set where you wouldn't really consider this a distribution. So in this case, we had people tell us a major reason they would find it difficult to quarantine themselves for at least 14 days. And in this case, they were allowed to provide multiple answers. So they could have said, more than one of these things. And so because of that, what's going to happen is if you add up all these numbers, they're going to be more than 100. And so you have overlapping groups. And so in this case, it's not really following our rule where you can only have exactly one response or kind of exactly one answer, right? And so these kinds of questions will be common. Like you can ask this in a survey, it's totally fine, but you just need to be careful when you're interpreting the results here. This isn't exactly a distribution here. There could be a lot of overlap. It could be the case that like everybody who responded with unable to miss work also did too many obligations. And so you might be sort of like double counting things, right? And there's ways you can get around it, but just be really aware what you're looking at. And if it doesn't add up to 100, it's not a distribution. Cool. So any questions about that before we continue? Okay, cool. So let's look at our first kind of distributions, which are going to be categorical distributions. So these are just going to be distributions of categories effectively. So we'll just head on over to our notebook here. So we're going to run that first line of code again, and then we're going to read in this data set, which contains all of the movies from as of 2017, I guess, all the top movies that grossed for every year. And so we have this is the same table that we saw last time. So we have like the title of the movie, the studio that made it, the gross earnings adjusted for inflation, and the year that it came out in as well. And so let's, for today, just focus on the studio column. So it might be interesting to get a sense of what is the distribution of the studios that are represented in this data set. Which studios tend to be making these top movies, right? And so we can go ahead and do this. So if you wanted to actually look at this, one thing we can do, first of all, is we can just select the studios column. So I'm just going to create something new called studios. We can just take top movies and select the studios column. So top movies.select studio. And then we can just take a look at what we have here. So if we create just this column, you can already kind of start to see, how often certain ones are appearing. Obviously, we're not seeing the entire column here, but we're seeing several rows of this. And if you wanted to see more, you could do this, right? Like I could say show like 50 or something. I could see a lot more of them. And you can kind of scroll down and like start to eyeball that like some of these are appearing maybe more often than some of the other ones, right? And if we really wanted to take a look at this, what we'd want to understand is, can we just see the unique values and how often each of them appears? That's what we're trying to get to. And thankfully, we can do this in Python. There's a new function that we're going to use to do this, which is called group. And here's how it works. So I'm going to call this thing studio distribution. And the way I'm going to create it is I just take this studios table, which just has one column in it right now. And then we do dot group. And we pass in what we want to group on. In this case, we want to group on studio. And we can see what this shows us. So if we run this, what it'll do is it will convert our entire table, which has over 150 values, and then it makes it a much smaller table. And here we have just all the unique values of Studio, and then it automatically creates a new column called count, which shows how often that Studio shows up in your original table. And so we can see that ABCO 1 time, Buena Vista 35 times, Columbia 9 times, so on. So you're getting your counts of how often each one's appearing. And we ran this on the table of just the values above, but you could actually just run this on the original table as well if you wanted to, and it will work the same way. And this is actually maybe a good opportunity to show you guys the reference sheet that we have on the website, which explains how different functions work actually. So I'll just show you this really quickly, and we'll actually look at what the group one shows. And this is really helpful in general when we're just working with different functions. You may not be familiar how it works. So if you just head to the website, we have this Python reference sheet here, and we have all the different functions that we're going to be using in the course. They're all going to be listed here. And you can see the name of the function, the description, which kind of just plain English, what does it do? What inputs does it have, if it does have any? And then what should you be expecting as the output here? And so if we wanted to find the group one, which is what we're using right now, I'm just going to search the page for group, and we go ahead and find it right here. So this is the function, group function, and it says group rows by unique values or combination of values. And then if you're going to use multiple columns, which is a little bit beyond the scope of today, then you have to put them in a different format. And then it's basically saying the input should be a string or an array of strings. In this case, we just used it as a string, 1 single column value, and then we get back a table. And so don't worry too much about the optional part of this. We haven't done this yet. But in general, this is really helpful. You can just use this to look up any functions and understand how it works. And it's just a good reference sheet because you'll be kind of expected to know all these sort of by the end of the course. And I mean, I should mention on exams, we'll have a reference sheet like this too, a little bit simplified. So you have to memorize all of them, but it's just good to know what they do. So that's what the group function does. So again, if you have a table, you just call group and then pass in what column you want to group on. It will just take the values in that column, return the unique ones, and then count up how often each one appears. And so this is one way to look at a distribution. This is essentially a distribution. This is the first distribution we're seeing in the course. And this is, we're seeing it as a table. Now you could maybe imagine how we could try to visualize this in a chart format. What we could do is we could keep all these same unique values here, but convert the counts into bars. So instead of seeing numbers, we could just see bars that are shooting out to the right. And that would be really helpful to do. And thankfully we can do that. We can do that using a bar chart, which is what we went over last time. So bar charts work really well for categorical distributions. It's kind of what we're always used for categorical distributions. And it works because if you remember bar charts, what are they for? They're for when you're trying to visualize something categorical against something numerical. So in this case, a distribution for category is all the unique categories. That's a categorical variable. And then the counts. Counts is numerical. So it kind of fits into what we need to do for a bar chart. And so if we use a bar chart here, what you'll see is you'll see 1 bar for each category, each unique category. And then you do have the ability to change the order of the bars, which we'll go over in a second. And then the main thing to remember is the length of the bar is going to represent the percent or count of individuals that's in that category. So if you go back out here, we can actually go ahead and create a bar chart for this. So I'm just going to take this studio distribution and then call bar H. So this is just from the last lecture. And then we do have to pass in what column we're talking about here as the category. So we want studio to be the category. And we can go ahead and run this. And then we get here a bar chart. So on the left, we have studio, and then on the bottom, we have count, which is the other variable that was there in this table. And so now it's a little bit easier to see them. So you can see like how much bigger Buena Vista is compared to some of these other ones. Paramount, for example, Fox, you might have noticed those were coming up pretty often as we were scrolling down the table. Now we can just see this really nice and easily visually here. Now, one thing about this visualization is that it's ordered alphabetically. So by default, our table is ordered alphabetically. And so that's why it looks like that this way. One problem with this is that it's a little bit difficult to compare 2 different studios that are maybe not right next to each other alphabetically, right? So if I was looking at, for example, I don't know, try to pick some random ones here, like Paramount and Sony, right? I can't quite tell like which one's longer. It's pretty hard to tell. The length of the bars are really similar. It's pretty likely they're not going to be exactly the same, right? But it's a bit hard to tell when they're ordered like this alphabetically. So one thing that's really nice and highly recommended to do when you're making a bar chart is to order things by the actual counts. And so then you can see them right next to each other. and then you'll be able to tell which one's longer than the other. And so if we wanted to do that, it's quite simple now with Python. We can run the exact same code, except we're just going to add one thing, which is that before we call bar H, we're going to sort our table. And so we can sort by count. And let's do descending equals true, because we want the tallest bar at the top. It just might look a little bit nicer that way. And so now we get something like this. And so if we go back to the two that we were comparing, which was Sony and Paramount DreamWorks, we can see them right next to each other now. It's still a little bit hard to tell which one's taller, which one's longer, but we know that the one on top needs to be at least as tall as the one below because we just sorted it, right? So we at least know that information. So that extra information helps a little bit. And so just a little bit easier to compare how often each one's coming up here. So any questions about this so far, how we made this visualization? So one question for you guys, why do you think, so you can see the different lengths of the bars, but why do you think the widths of the bars are all the same? So when I say width, it's kind of like the shorter piece of the bar. How come all of those are like the same going all the way down? Like we could have just made them whatever width we wanted. Maybe we could have made them different widths. Anything that makes that useful for us? Yeah, I mean, maybe it's just because it's a category, it's a number, it's not a number. So that's true. But even just, I guess, from like a fundamental, just like visualization perspective, like why might it be helpful when you're trying to visualize these different categories to have them all have the same widths? Yeah. Yeah, so if you see a bar with like a different width, then it may not be as easy to compare, like which one's bigger than another, right? In this case, it's really easy because I can just go ahead and say, okay, I know this one's longer than this one, so it appears more often. It's more frequent in the data, right? So your comparison is just really simple if you do it this way. So that's the main reason. So when you have categories, there's no reason to really do anything fancy. Just keep them all the same width, and then all you need to look at is the length, and then just compare lengths, and then you know which one's more frequent than the other. So it just makes your comparisons a little bit easier. Cool. So that's how we can visualize categorical distributions. Very useful technique. It's just really, really helpful to do this when you're looking at your data. One really common way that you'll use this actually is like if you're taking a survey and you're trying to make sure like certain categories of individuals are represented properly in your survey, right? You could check that really easy with this. You could see if you have anything wrong, like maybe you sampled too much from like a certain part of the population or something like that. So there's just lots of reasons why this is really helpful. And then besides that, I mean, there's lots of interesting problems that have to do with categories. A really common one when you're polling is just like who is being voted for, like in an election, right? You might have several candidates that are running, and so you could see what percentage are people voting for. That's another example of a categorical distribution. Cool. So now let's go to numerical distributions, which are a little bit trickier. So with numerical distributions, what's a little bit funny about them is that I want to create something similar where I want to be able to see some bars over different parts of the data. And I want to see what values are more common than others. That's fundamentally what you're trying to answer when you're creating a distribution. But the problem is if I'm trying to make these bars on top of my data set that's numerical, and there's like infinitely many possible values, then it may not really make any sense. Like if I'm asking, everybody in data A, like what's your height, and you give me your height up to like 6 decimal places, almost everybody's going to have a completely different answer. So if you're trying to create that list of unique values, everybody has unique values. And so everybody's just going to have like the same height of their bar in this visualization. And like, that's not really telling me anything interesting. It's very difficult to make any sort of understanding out of that. And so what we're going to have to do with numerical values is we have to find some way to group them together into a smaller set of categories. And the way we do this is by binning. And so what we're going to essentially do is we're going to take our entire range of our numerical data of a particular column and then set some increments, which we're going to call bins, and then just put our values into those bins. And by doing that, we essentially are making categories out of this numerical data. And then it's a little bit more straightforward how we can actually make the bars in the visualization. And so the way we're going to define our bins, they're going to be defined by their lower bounds. So that's like the left part of the bin. And then the upper bound is going to be the right part of the bin. And it's not going to include that. So if that doesn't make sense, don't worry, I'll explain it again right now. So for example, let's say that our column of data looks like this. So we have some column and it has values like 188, 170, 189, and so on. And so if we wanted to make some sort of distribution out of this and actually understand like are values around 180 more common or are values around 160 more common, one way we could do that is we could make bins that look like this on the bottom here. So we could have our bins be 160 to 165, 165 to 170, and so on all the way up to 190. And then if we wanted to actually put actual values in a bin, we could basically go through every single one of these numbers and then just assign them to their relevant bin. So for example, the value at 188, that would get assigned to this bin because it's between 185 and 190. The 171 would get assigned to the 170 to 175 bin, which is this one right here, and so on. And the way that we will kind of write out these bins is you write it like this. So you put a bracket on the left and then you say 185, comma, 190. And on the right, you put a parentheses. The reason we do this is because the parentheses means that it doesn't include the number on the right. So you start at 185, and you include every possible number, including decimals, all the way up to 190, but not including 190 itself. So if you had like 189.999, you'd still put it in there. But once you get to 190, that needs to go into the next bin. And so that's why 170, for example, is in this bin rather than this one. And so for consistency, we're just going to define it this way always. So whenever we're making bins in this course, the left number is included, the right number is not included, everything up to the right number. And so we could just go on, continue like this, right? So 189, which bin is that going to go in? You could just say it out loud. The last bin, sure. 163, which one's this one going to go in? First one, yep. 183. Second from the right, yeah. 171, how about this one? Third, 185. Last one. Yes, that one's a little tricky, right? 185, make sure it's on this side. 168. Second, all right, 173. Third, all right. So now we can see we've now binned these values up, and now this is starting to look a little bit like that bar chart, right? And so now we can sort of take a look at this and like start to get a sense like, okay, so there's a lot of values around 170 to 175, a lot of values around 185 to 190, not as many values outside of those ranges, right? And so this is kind of the best way we can sort of actually make a visualization when we have these numerical data. It's just going to be a lot more interesting this way if we can bin it. And imagine if we didn't bin it, you know, and we were just using like bins of one or something, right? Like you would just have the same length everywhere. And it's like, I have no idea what this means. It's not really giving me as much information. So it's really common that we'll do this that way. And this is especially important when you have decimals. If I can go to several decimal places, then I need to bin to actually show anything interesting. So let's see how we would do this in Python. So we can take the same data sets. And in this case, let's try to look at the distribution of the age of the movies. So if we go back up here to the original table, the one numerical variable that we have is the year that the movie came out. So any thoughts on how we could find the age of the movies if I know their years that they were released? How could we maybe create a new column that contains the age of the movies? Any guesses? Yeah. Yeah, exactly. Yeah. Yeah, exactly. Yeah. So one way we could do it is we could take the current year. So for example, it's 2022, and then we could just take the difference to subtract the column of the year where they came out, right? So for example, this first movie, Gone in the Wind, came out in 1939. If you want to know that its age as of today, we just take 2022, subtract 1939, and that gives you the age. And then we could do that for all of these really easily because that's how, with arrays, it's really simple. I can just take this entire column as an array and just subtract it from the number 2022. So let's just go ahead and do that. Just show you how we can do this in Python. So I'm just going to call the result ages. So we can just do 2022 and then subtract that column, top movies dot column year. And so the nice thing about Python is that, again, this is an array of values. So this has several values in it, like over 150 values. And this is just a single number, but it knows it's smart that when I'm doing this, it knows it's going to do 2022 minus every single value in the array. And so the result is going to be another array, which has the ages that we want. And then we just add it back into our table. So we're going to do top movies equals top movies with column. And let's just call this age. And then it should contain the data inside the array ages. And then we can just take a look at our table now. And so now we've gone ahead and added age as another column here. And so, for example, Gone with the Wind, now we can tell 83 years old. So now we have this in the format that we wanted, which is ages. And so the next step is to actually bin this information. So if I wanted to make some bins for this, just looking at the table like this, I don't really know exactly how I would do that because I don't really know how, like where these values go. Do we have a movie that's like really, really old in here? Do we have a movie that's within the last 5 years? I can't quite tell just by looking at this. So one thing that's good practice to do before you go ahead and try to make your bins is get a sense of the range of your entire data. What is actually going to be the smallest value? What's the biggest value? And if anything outside of that, I don't need to worry about that because I know the data only goes up to those limits. And we can do this really easy with the min and max functions. So we can look at min ages, in this case, it's 5. And then we could also look at max ages. And in this case, it's 101. So we can get a sense of the range now. And so now I have a kind of a sense of like where we would maybe want to do our bins. And so let's go ahead and just make up some set of bins here. And I'm not necessarily even going to make these evenly spaced, and that's totally fine, actually. We'll see why in a second. So I'm just going to make some ranges here. So let's do 0 to 5 is the first one, then 5 to 10, 10 to 15, 15 to 25, 25 to 40, 40 to 65. And then last one we'll do 100. Actually, let's do 105. And so now we have all of our bins here. And then if we wanted to actually split up our data into bins and look at how many movies there are within each bin, we can do that using the bin function. So I'm just going to call the result bin data, and then this is going to be top movies.bin. So here's our new function. And then the way the function works is we call it on our table, and we pass in what column do we want to bin on. So very similar to how we just did group, right? With group, we did .group studio. Here we're doing .bin age, but we need one extra argument here, which is the actual bins. How should we be grouping this? We have to specify some more information here. And so in this case, we'll do it with that array that we just created, my bins. And now we can take a look at what this has. So we see something that looks really similar to the distribution for the categories, except now this is talking about numerical information. And the way to interpret this is basically we have 0 to 5 that has 0 movies in it in that bin. Then we have 5 to 10 that has 25 movies in it, and so on. And then finally 65 to 105 that has 21 movies in it. And then you should expect to see 0 here because this is just kind of like the end of the range. So this, you might have been a little bit surprised if you saw that this was 0 here because we just saw that the minimum age was 5, right? But the reason for that is, again, because the bins are defined from the left side. So they include the number on the left. So the first bin is 0 up to, but not including 5. So 5 gets pushed over into that second bin there. So that's why there's nothing in the first bin. But overall, now we have basically done the same exercise on numerical data. And so we have a sense of the distribution here. And so, you know, a lot of the movies are kind of 5 to 10 years old, but then we have even more in this range here from like 15 to like 65 years old. And then not that many after 65 years old. Yeah. Yeah, you can totally use a range here as well. So instead of this, you could have done like np.range. You could go like 0 to 105 in increments of 5. That's totally fine too. And then you'll get something a little bit different. But you could do that as well. Yeah, so that's totally fair. Any array will work here. Yeah. Cool. So yeah, I mean, you might be wondering like, why would we ever do this? Have ranges of like different widths. Like this one has a width of like 25, whereas this one just has a width of 5. So it's like a little bit strange, which I'll explain in a little bit. But basically, as we go on in the course, we'll see more and more examples of this. And you're not necessarily going to always see visualizations where everything has the same bin width. So it's just good to kind of get used to being able to interpret that. Cool. So now that we've actually seen a distribution in numerical data, the last step now is to actually make a chart out of this, just like we did in the categorical case. But before we do that, there's one sort of thing we have to cover really quickly, which is the area principle. A few people sort of alluded to this. And this concept, this is a good picture that maybe explains this concept well. So this is from several years ago. This was showing like when the new iPad came out, and it was saying that the caption basically says the new iPad battery is 70% bigger than the previous generation. So 70% is like almost, meaning like it's almost twice as big essentially. So this is the actual battery itself, not like battery life, like literally the physical battery. So that was the caption, and then this was the graphic that they used. So look at this for a second and just think like, do you see any issues with this graphic? Anything problematic as it relates to the caption? Yeah. Yeah, so in general, if you see that it's saying it's 70% bigger, you would expect sort of this graphic on the right to be 70% bigger, like roughly twice as big, because 70% bigger is like 170%, so it's almost 200, so it's almost twice as big. But what's happening here, if you look at this, if you just sort of eyeball it, it's looking like this battery on the right's twice as wide and also twice as tall. So if you look at the actual area of it, it's actually almost 4 times bigger. So it's like 4 times the size of the battery on the left. So that's where it gets a little bit strange, right? And so then it's making it seem like it's a lot bigger than it really is. And in general, when you're making visualizations, we're limited to a screen. We're limited to kind of 2 dimensions on our screen here. So you want to be trying to think of areas as reflecting relative values here. And so when you have something that's twice as big, it should be literally twice as big. It should not be 4 times as big. So that the area needs to be twice as big. That's just how our mind is also going to perceive it too. It's just more intuitive and more accurate that way. And so like a simpler example is, if you're representing like 20% of some population by this little triangle, then 40% should be represented by something that's like 2 triangles. So it's like twice the area. It shouldn't be represented by a really large triangle that's like twice as wide and twice as tall, because that's actually going to be 4 triangles. So it's a lot bigger. So just really important that we do that. And this is important to understand because this is how we create histograms and how we interpret histograms as well. So when you see a bar that's maybe not the same width, that's okay. Just look at the area. The area is what's going to tell you the relative size of things and the relative frequencies of those kind of ranges of values. And so we'll take that same kind of philosophy to drawing our histograms. And so histogram is really just another term for the chart that's used to visualize the distribution of a numerical variable. All right, so we use bar charts for categorical distributions. We use histograms for numerical distributions. So let's take a look at how we actually can make a histogram. So we're just going to use these same bins again, which have different widths, again, just so we can demonstrate this a little bit. And then we'll also take a look at our data as well that we're going to be visualizing. So this is just that table that we made, which kind of grouped our data into these different ranges. And then one thing we can do before we even make the visualization is it might be good for us to just get a sense of what percentages we're going to expect to see here. Because right now we're seeing counts, but it'd be nice to convert this into percentages. And so one way we can do that is just divide all the numbers here by the total counts. And so there's 200 movies in this data set. So what we can do is essentially, if we wanted to convert this to percentages, we could do bin data.column age count, and then we can just divide that by 200. And we'll multiply it by 100 just so that our numbers look a little bit nicer here. And so 25 corresponds to 12.5% of the entire data set. 16 corresponds to 8% of the entire data set, and so on. So that's all we did. We just took each value and divided it by the total there. And then we could add this back into the table as well, just so we can see it all together. So we can do bin data equals bin data with column, and then we can just call this percent. And then inside percent, we can just put this same set of information here, this array that we created. And so if you look at all of that together, now we have the original bins that we had, how many movies there are in each bin, and then what percent does that correspond to of the data. So this is just helpful to see because we're going to make the visualization now, so you'll be able to check it back and forth. So how do we actually make this histogram? How do we actually visualize the numerical distribution? We have a new function. It's called hist. So it's just an abbreviation for histogram. And the way we run this is we just take our table, call hist on it, pass in the variable that you want the histogram of. In this case, we want age. And then how do we want to split up age? We want to use some bins here. So you have to specify that as well. Bins equals my bins. And I'm just going to add one more argument, which will just show us the units on the x-axis, because by default, it doesn't actually do that. And so we get something like this. So essentially what this did was it took the entire table, all the ages, the age column, split them up into these bins. So it's doing several steps here. So it split them up into these bins that we specified here with this array. And then finally, it calculated the percentages and then created this visualization right here. And so you should see the numbers that are here. would correspond to the numbers you're seeing here with percentage in terms of the area that's being represented. So this one up here, for example, it's the tallest one, but area-wise, it's not necessarily the biggest one. So these ones are much bigger area-wise. That's corresponding to this one. So this one's 20% of the chart. This one's 21%. This is 28% of the chart, this bar, and so on. So the numbers here again are the percentages in each bar. And so now we have a way to actually visualize frequencies relatively across a numerical range rather than just like categories. And then one other interesting to do might be to look at this in terms of using bins that are just evenly spaced. So we can use arrange to do that. So we can go, let's say 0 to 110. Let's do increments of 10. So all I did is just replace the bins that we created up above with just some evenly spaced bins. And then you can look at it that way too. And so if you think about both of these, you can kind of interpret them in the same way. They're sort of giving us a lot of the same information. But there could be reasons that you might want to do it this way. It just depends on what sort of story you're trying to tell and what are you trying to put more of an emphasis on. But they are showing both the same information actually. Yeah, any questions in the back? Oh yeah, why do we divide by 200 and multiply by 100 again? So we divided by 200 because there's 200 total movies. That's the total number of accounts, basically. So if you summed up all the values in this column, that would be 200. So if I'm trying to convert each of these values into like what percent are they of the entire total, that's what I need to divide by 200. And then we just multiplied by 100 so that the numbers would look a little bit better. If I didn't do that, then you'd see like decimals. So I was just trying to convert decimal to percentage. Yeah. Oh yeah, why is the percent per year 2.5 on the bottom here? Is that what you're asking about? Yeah, so I guess this leads well into the next part, which is that if you think about this chart, area represents percent, all right? So just remember that. So the units for the area of any of these rectangles is percent. And then on the x-axis here, the units are years because it's age, right? So the width of any rectangle is represented in years, its area is represented in percent. And so therefore the length needs to be the area divided by the width because you have width times length is the area. And so I'll just write this out here actually, this might be a little bit helpful. So, area is percent and then width is years. And so what does the length have to be? Well, if we think about it, we know that the width times length is equal to area. And so if we know that this is years and this is percent, just do some algebra here, the length needs to be percent per year. And that's why we get that as units here for the length. So it's a little bit funny, but the reason it's just so that if you multiply these two things, the x-axis times the y-axis, the result is percent because that's what we want the area to be. So that's why it's doing it that way. Now the interpretation for that we'll go over in a second, but that's the reason that it's defined that way. So just to recap kind of histograms, this shows us the distribution of a numerical variable. We have one bar corresponding to each bin that we create. And the key thing is to use the area principle when you're comparing any two bars. So area of the bar is percent of individuals in the corresponding bin. And this is really the real reason why we use differently spaced bins is because as we get into later parts of the course, we're going to start to approximate these bars with actual curves. So rather than seeing like these different bars that are all separated out, you're going to see a nice smooth curve. And so you can imagine this even over our data set here. Like instead of this, imagine there's like a nice little curve that just goes through the middle of all these bars, right? You can still think of a distribution in the same way, but it's helpful because when you have these different smooth curves, you might have some parts that are flatter, some parts that are steeper. And so this just helps you prepare for that sort of a setup. So don't worry about that right now, but that's kind of where we're going towards the end of the course. But the key thing is what's really nice is even once we get there, area still represents percent at the end of the day. In this case, it'll just be like area under the curve represents percent. It's the same thing, except now we're just doing areas of bins. So yeah, one thing on the axes, area of each bar represents the percentage that's contained in that bar relative to everything. Your horizontal axis is going to be some sort of number line. In our case, it was years. It could be whatever unit is relevant to the variable that you're actually using. And so because of this, the vertical axis, you can think of it almost like a rate, or like it's called density is another way to think of it too. In our case, it was percent per year. So it's the reason it says rates is because anything you think of like this is called a rate, like miles per hour, right? So percent per year, that's all it's really saying. And so if you wanted to calculate the height of a particular bin, for example, the 40 to 65 bin, if you wanted to figure out what is the actual height of this, you could calculate this using the percentages and the width and just working your way backwards. So for example, the 40 to 65 bin, it contains 56 out of 200 movies. So if we just go back here, we can just double check that. So 40 to 65, 56 movies here. So 56 out of the 200 movies, that corresponds to 28%. So now we've calculated essentially what percent should be that area of that bar. We know the width of the bar is 25 because that's just 65 minus 40. And so therefore to find the height, you just divide both of them together. So 28 divided by 25 gives us 1.12% per year. And then if we go back here and go to that bar, 40 to 65, it's essentially saying the height of this is going to be that same value. And so that's how you could actually calculate the height of the bin. So again, you're just kind of using that algebra to figure out what the height is. And so how do we actually like interpret this? It's kind of weird, percent per year. What does this really mean? So really it's just telling you sort of like the relative amount of space or like crowdedness in that bin. I really like crowdedness. I think that's like the most intuitive for me personally. And so if we just go back to this graph, what it's basically saying is like, this chart has like a lot going on as I go from left to right through this range, but then it has a lot less going on as I go to this range, and then even less as I keep going to the right. So basically, like as you go left to right, like is there like a lot of stuff happening there or not that much stuff happening? That's essentially what the height is telling you. And so, you know, percent per year, it's like there's a lot of percent of our data is happening per year as I go left to right and for these years, but then not as much happening per year as I go through these years, 65 and beyond. Right, so that's how we can actually interpret what that means. Yeah, and then I guess one last part on this is just if you're trying to answer the question like how many individuals are in a bin, then you should just use the area. That's what's going to tell you. Whereas if you want to understand how crowded is a bin, then you use the height. So this is a really important distinction because this is not the case for a bar chart. When you have a bar chart, area and height mean the same thing because they're always going to have the same width all the way down. For numerical data, that's not going to be the case. So just remember that distinction. It's a little bit different there. So area means individuals basically for both of them, but height means something very different in numerical data. So we'll maybe skip this question. Just wanted to show a couple more examples before we finish. So this is the actual welcome survey. So let's actually take a look at this. This is kind of fun. So if you remember, we have all these different variables here. So we have like the year, extroversion, number of textees, and so on. And so we could actually take a look at this and try to look at some distributions here as well. So for example, if we wanted to look at the distribution of hours of sleep, we could do this. So I just made some ranges here, 4 to 11 as our bins. So I'm just using a range to do this. So these will just be default increments of 1. And I'm just calling the function the same way we've already been doing. So welcome survey.hist, I'm passing in hours of sleep. And so we should take a look at the distribution here. And so we see something like this. So most people are getting between 7 to 8 hours, which is good. And then a few people even getting beyond 9. And then a few people getting as little as 4. So, you know, try to get some more sleep there, please. But you can see the distribution here. And then we could do the same thing for like extroversion, for example. So that's another numerical attribute. You could take a look at, you know, how is the class distributed in terms of introverts versus extroverts. So any guesses on this one? Like, do you think we're going to have a lot more people who are more extroverted, a lot more people introverted? Any guesses? Any thoughts? A lot more introverted. All the extroverts are the ones who answer, right? Okay, so let's see. Yeah, that's kind of interesting. So, you know, this 5 here is kind of like the middle point, I guess. So it's actually slightly more extroverts, it seems like. But we do have a lot of area here, right? Like these 3 bars, there's a lot going on there. So you can see that. And then there's like basically nobody beyond 9. But you do have people as low as like 3 on this side. So it's kind of interesting to see the differences there. One other one which I thought was kind of interesting is to look at a categorical distribution of the pets. So this one's a little bit funky because the responses, you could have just put whatever you wanted. So we're going to have a lot of unique values, a lot of like very rare unique values, but you can just see what happens when you do this. So we can look at a categorical distribution of pets. And this takes some time to run because there's a lot of responses. But let me just zoom in a bit so we can take a look at some of these. Yeah, so we have so there's every semester there's a few people who are brother. We have cat, dog. So it's interesting, like cat, dog comes up as its own category. So this is one way that you can actually handle a situation when there's like multiple responses allowed. Dog is like really common. This person just has a lot going on. Yeah, this is just some like really long ones. Yeah, this one was very interesting. I think it's worth reading aloud. So this is kind of a sad story. So apparently, like one of the fish ate the other fish, even the bones, and then they named the other fish Shredder, which is named after Teenage Mutant Ninja Turtles villain. And thank you for your time. So, yeah, you're welcome. Good answer. So, anyways, it's just kind of fun to see like all the unique values here. Yeah. 5 younger siblings, yeah. So that's just not the brother, it's just all of them. So yeah. So anyways, you can just see the responses here. You guys can do this yourself too with the data set. It's just kind of fun to look at. So yeah, I guess just to recap at the end here, one last thing. Just want to compare these two. So bar charts for categories, histograms for numerical data, and just remember what the different axes mean and what area and height mean. Those are just this chart's probably the most important slide of the lecture. All right, thanks everybody.